if you're following the slope lines, did your graph end up looking very similar to my graph? And it's somewhat impressive that it's not hard to do to follow the slope lines, and that all of our graphs are almost identical. They're very, it's hard without, like, literally not following a rule to not get a line to look almost identical to this. The slopes tell you where to go. And unless you don't listen to them, your graph is going to look like this. So, identify the particular solution that goes through the point. So the figure to the right shows the slope of the slope field for a differential equation. Sketch the graph through 0, 2. Right, that's part A. Label that part A. Sketch the graph for a particular solution through -1, 2. That is point B. Whew. That slope field, does that make you, the way that it printed out on your page, doesn't it make you kind of get dizzy? Makes me think of making up a little game. If you started on the left side, and your goal was to get to the right side as fast as possible, like a little amazing race for slope fields, or no such a thing exists. Which one looks faster? Which path looks shorter, path A or path B? Or are they about the same? Where should you have started? This forces this one up more. They actually look like they start at a very similar spot as a result. Which is interesting, because here, if you had started here, this could be where it'd be hard to draw it. You have some choice there. Tiny little differences at the edge of the graph on the left seem to make big differences as you go from left to right. But where we started, it was pretty obvious what we needed to do and where it needed to go. So we've got our slope field. Which of the following could be a solution with the initial equation 0, 0? So the only thing we know for sure is that point. And having that point gives us that part of the graph, but it really didn't give us anything on this part of the graph. But those straight vertical lines, those slopes that are undefined, form an asymptote at x equals -2. So we have some possibilities here, actually. Right away, you could cancel out C. This is the first one I would cancel out right away, because that one does not have a vertical asymptote at x equals -2. But these other graphs do. These other graphs have a vertical asymptote at -2, and -2, and at -2. So this becomes a bit of a challenge to figure out which graph is which. Okay? So some things that you would use from previous knowledge to figure these graphs out. Okay? Do you notice that this one should have a horizontal asymptote at y equals 0? If you did the limit as x goes to infinity, the power is bigger in your denominator. So that graph should have a flat line at y equals 0. Do our slopes look like they flatten out at y equals 0 as it gets bigger? No, they look like they're getting steeper. So that would be a way to cancel out this one. So now we're down to 2 left. And we're sort of using a technique here where we're thinking about each graph, and if we notice something that doesn't work for it, we cancel it out. So next one, how do I know to cancel out b? Well, on the top of b, I have tan of x. And tan of x is undefined at certain values, right? On our pi plate at pi over 2 and at 3 pi over 2 and negative pi over 2, tan is undefined. So if something is undefined, it would have those vertical slopes again, or it would have an asymptote. So I would look at pi over 2, which is 1.57. That's right about here. It does not look like my slopes are undefined at that point, so I could cancel out this one. Finally, I should do some checks here on this one to make sure that things actually match up. Okay? So, for example, how would I do some checks to see if things actually match up? I could take a point, like when, according to the graph that I've drawn here, it looks like I have a point very close to 3, 2. Okay? Well, and if I plug in 3 for x, I would get 9 over 5. Does that match up with 3, 2? Pretty close. Because 9 over 5 is 1.8. So that I could do a couple of points here. I could check, do these values actually match up? With this asymptote here, from my slope field, I actually can't tell this at all. That part that's circled in the green, that matches up with graph D, as far as graphing, if I would actually graph the function D, it would match up. But if I was just given the initial condition of 0, 0, and I run into an asymptote, I don't know this part on the left. I would need another point in order to be able to for sure say that. So that part of the graph, we actually could not officially state this is the one that matches up the best, and because this matches up the best, we could say, I graph this, it has this part in it. Okay. I don't know if you remember from your rational functions in grade 12, if the degree is bigger on the top, then this is a chance for an oblique asymptote. And this equation, part of this graph would probably end up looking like this in the bottom corner. I don't know if you remember those oblique asymptotes or not. Again, here's an example of a slope field problem-solving question where you use stuff that you know from the past about each equation, and that helps you narrow down and figure out which is the one that fits the best. And our last question here, consider the differential equation dy dx, x plus 1 over y, and its slope field is shown. describe all the points in the xy plane, y not equal to 0, because y equal to 0 is not allowed, for which dy dx equals -1. So if we look on our slope field, we're looking for little lines where the slope is equal to -1. Circle those all right there. That means that our our differential equation, if we know the slope is equal to -1, we can replace that dy dx with the -1. Which creates an equation. You can multiply both sides by y, rearrange it, and you have a line. Y equals mx plus b, y equals -x minus 1. Does that match up with this line? Sure looks like it does. So all the points on that line would be where your slope is equal to -1.